Here it comes. This absolute beast from HP, which is my cluster in the box. HP edition. What do you think? I'm going to walk through a scenario with you. I need to store approximately 250 to 260 gigs of data that has to have fast access to the actual data from the clients. Okay, so I can store the data on disk, but that's slow. Okay, on a regular spinning SATA disk, I can only read data about 100 megabyte a second. Okay, I can store the data on SSDs. That is significantly faster, but the fastest access is going to be in memory. So if it's determined from the organization's perspective that memory, storing the data in memory is the way to go, then what type of system could I build to store comfortably, to read and write without performance issues on the server, approximately 250 to 260 gigs of data. I'm going to spec this out on the board. So I'm going to utilize some blades that I have. So this is a BL490G6. I'll spec the configuration of the blade. I'll spec how much data I can put in, and you're going to see very, very quickly that it's pretty expensive to store a relatively small amount of data, 250 gigs, 260 gigs of data. Remember, you can buy 1 terabyte drives now, SATA drives, for approximately 50 to 90 pounds. Yeah. So when I spec this out, I think you're going to be very, very surprised. First, I'll ask you the question: how many servers do you think requires to manage 260 gigs of data in memory? This is in production, not on your desktop, in production. The answer, actually, let's calculate it out. So we're going to use a Java. Now let's assume Oracle Coherence as an example. So let's assume that you have a BL490 G6 blade. Okay, this blade has 18 DIMM slots, and let's assume 8 gigabyte DIMMs. Okay, let's do a rough calculation. So this is per server. This one I'm doing right now. So 18 times 8 gives me 144 gigabytes stored in the server. But I'm going to reserve 10% for the OS, for the operating system. So I'm going to times that by 0.9. So that gives us approximately 130 gigs that I can utilize per server. Okay. So I'm running Java processes. So if I assume Oracle Coherence, for example, or even Apache Ignite, and I'm going to mention a keyword which you may not know, I'm going to utilize off-heat memory. On-heat memory, not off-heat memory, on-heat memory, because usually if we actually want to download a lot of this stuff and run it for free, or have the basic pricing, it's going to be on-heat memory. Yeah. So given this, one of the things, and this is the shocker, the 130 gig that you have access to on the server, you have to divide it by 4. 130 divided by 4, and this gives you the amount of data you can actually store on a server. Now, why divide by 4? Because each server will hold a piece of your primary data, the data you've inserted in. There'll be a backup copy stored on the server from another server. Okay, so we're talking about multiple servers here. So there'll be a backup copy. Okay, you need space for working memory. So when you have calculations occurring within the Java process, okay, you need a buffer for that calculation to occur, and you also need space for garbage collection. So unlike like a language like C++, where when objects need to be removed from memory, the developer has actually stated, or actually coded in, remove this from memory. Okay, with Java, the developer doesn't do that. The Java process or JVM keeps track of objects that's been created, and when it actually sees that there's no references to the object that's been created, the garbage collector at regular intervals kicks in to clean up the actual Java process. Okay, but you need space for this to occur. Okay, it needs a buffer again. So look at this. So you've got 4 areas: primary data, backup data, working memory for calculations, and GC, garbage collection, to clean up the actual process. 4 areas. So therefore, this is the total memory space on the server, 130 gig, and hence I've divided by 4 because this is the area of data that you're actually inserted into the cluster. Yeah. So now we've determined that each server can only house 32 gigs, or let's say the capacity per server is now 32 gigs per server. So given that, 32 times 8 gives me 256 gig. And there you go. I need 8 servers to serve 256 gigs of data in memory to clients in production. In fact, it's actually times 2, because you also have, if you really want this high availability, you also actually want it in another data center. So we're talking disaster recovery here. So if you completely lose power in one data center, clients can then access. So you can have one data center here, and this can be, let's say, London, and you can have another data center here. Let's say this is Manchester. Basically, all your clients are around, your clients are here. They may access this data center here in London, but if we lose power here, this can then access the data center in Manchester, where it continues operating. Okay, so here you need 8 servers at this location, and you need 8 servers at that location. Hence, you now need 16 servers. So it becomes a very, very expensive piece of technology to serve, right? So think about a regular SSD, 256 gig SSD that you can buy, probably brand new, for between, let's say, 100 to 200 pounds. Yeah, for a very, very good make. Okay, here we're now trying to serve the exact same amount of data in memory, and now you're looking at 16 servers to serve it based on this particular model number. Yeah. So it's pretty interesting, right? It's pretty. Okay, so I'm just going to grab a couple of these BL490 G6s, so you can build our cluster. And a couple of these guys. All right, let's start cooking. I need another 4 more. Guys, so again, these can go up to a maximum of 24 hyper-threaded cores, BF490 G6s. What do you think? Pretty impressive, huh? So this guy has 16 bays, 8 along the top, 8 along the bottom. Right now I've populated it with 8 HP BL490 G6 blades, and these are G1 blades of the 460 configuration or category and stuff. Here we have 6, is it 6? 1, 2, 3, 4, 5, 6 power supplies here. And let me pull one out for you. There you go. So that's where the power supply goes. I mean, look at that. Look at that. Look how long it is. Look at my arm compared to that. That's pretty long, right? So 6 power supplies. Again, blades of various configurations. Okay, and let me show you the back of this guy. So just rotate this. And here we go. So we have, whoops daisy, oh shit, slightly, there you go. So what you see here is 10 fans, 5 along the top, 5 along the bottom. I'll take one of these fans out. That's what it looks like. Yeah, it's almost like a jet engine. Look at that. Look at that. Yeah, it's pretty impressive technology, to be honest. And these fans are hot swappable. So if one of these fails in the actual data center, you can easily just pull it out, and the whole chassis keeps on going. So these are the fans. These are actually the connections for, out to the power supply. So these we connect. You can actually have dedicated switches internally here. The switches occur inside. So again, the blade connects inside here. The switch goes inside here. There's a mid plane right here in the middle. So traffic from one blade will come here in, hit switch inside, and then go back in. Okay. If you actually want traffic to go to the outside world, that is where all these fancy connections are. So these will go out to a traditional Cisco or HP switch to be switched up at the core. Yeah. So if you don't want switches here, because some people don't want to configure twice, you don't want to configure a switch here and also configure it at the core. What you can do instead is have a module. So do I have one here? No, I don't. These are all switches. These are all switches. But you can insert a module instead, and all that simply does is pass the traffic out from here up to the core. Okay, there you go. This is the HP, well, my one anyway. Yeah. Oops. Jesus, it's heavy. Scratching up my table here. Yeah. So there we go. So there's my plus in the box. You saw the quick video of me inserting this stuff in. But again, let me show you the internals of one of these 490 G6 blades. So if I open it up, I'm going to show you this guy. This guy's not configured. So here you have, again, various MES cards that goes in here. We have the SSDs that sit here. We have the CPUs. Again, maximum of 24 hyper-threaded cores, so 6. Real cores, so it gives you 12 cores, hyper-threaded, so that's 24 cores, and that's it. So let me actually put this lid back on. So put it back on a lid on a HP blade, to me is far easier than put it back on a Cisco UCS blade. There we go. So simply slot in. And there you go.